Welcome everyone. Today we are going to discuss about a new topic from the tool design drawing subject, and the topic is the split cavity mold. Let us discuss about the design context to begin with. Now take a look at this part here, this part. So simple, straight walls, it's a straightforward part, nothing complicated in this. Now compare this with this part here. This, you can see an undercut here, right here. See, an undercut. This undercut is going to create issues when you open the mold, right? So like this is a screwdriver head. See, this is screwdriver head. Now since the hole is on this side, it will be mounted this way in the mold. Now this portion belongs to the cavity, and just picturize yourself. Just imagine the core is getting withdrawn. It is supposed to, see, the core is supposed to carry the component along with it, but it's not going to come out because this portion here will get trapped in the cavity because the big diameter here is small, again a big diameter. So it's an undercut here, right? So this is the context that demands us to design a split cavity mold. Now let me share the screen here. Let me put this into the slideshow. There we go. So this is a split cavity mold chapter, and the design context is, we have already discussed on it. We have seen the sample parts, and this is one of those, the example where you have the undercut. For the discussion's sake, let us consider another simple part. What you see on the screen here is a pretty square part here, 30 by 30, and it's having an internal size of 26 millimeter. That means it got a wall thickness of like 2 millimeter per side. So it's having a wall thickness of 2 millimeter, 2. And the other design inputs is not given here. Let us provide that. The material can be polycarbonate, that is PC, and you need the shrinkage value for this. Shrinkage should be 0.5%, and of course for discussion's sake we need the number of cavities too. Let us consider number of cavities. There's say take it as 2. Okay, now just like the sample component which we saw, this portion here is going to give us trouble, right? Because it is a undercut. If we go for a traditional design, like a two-plate mold, this component will get trapped inside the cavity in this area, right? Let us have a look. So need for a split cavity design arises when the part is having a external, and this word is here is important. It's external undercut, right? So this, let us go into the design concept now. So this is what is going to happen when you go for a traditional design like a two-plate mold. Now, just watch this. Watch this portion here. What will happen when the mold opens? See, when the mold opens, the component which is supposed to sit here, right? The component is supposed to sit here, but it did not. Usually it gets shrunk onto the core and the core will pull it out. In this case, because of this undercut here, the component got trapped inside the cavity. Now, how we can take this out? There's no way. No way. But we got to overcome this situation somehow. So this is where we are going to split the cavity block into two pieces. See, you cut this into two pieces. This is piece on the left side, and it has become two pieces now. So this is how we derived the name split cavity as derived. It's called the split cavity. So this is what a split cavity is. So now we should get into the detail. You have split. Now we have cut the pieces into two. So this piece can be pulled out this way, moved out this way. One on the left can be slided out in this way. So the piece is free now. It is out of this undercut catch, right? A closed condition, spread apart. Now the component can be moved out. Now we have already decided to split the core into two pieces. Now, how are we going to put this into action? You can't expect the operator to take this splits every time and then remove the part, again put it back. It's going to consume a lot of time, right? We will be missing the, compromising the cycle time. So we have to make some arrangements to may slide these splits by some means. Let us see what are the methods. There are a few other methods. Sometimes if the moment what you need is very small, you can use a spring loaded actuation. And sometimes some cases when you need too much of travel, you can use a hydraulic cylinder. But let us ignore those two for the moment. Let us see traditionally how a split is moved. See this pin here, which is mounted at an angle in the top plate. The plate's on the top. This pin here, just imagine the plate is moving up here. It will move from here, right? So what will happen? When this pin is mounted at an angle, if it were mounted straight, nothing is going to happen on the slides. It will just draw out of the hole. Now the pin is mounted at an angle, and the same supplement, the hole cut in the splits are supplementing the same angle. So when the pin moves up, it will pull the slides to the side, right? And what should be this angle is a question. So basically the concept is pin mounted at an angle. Also it is engaging in the same supplementing hole in the split. When it moves up, it has no choice to other than pushing the split to the side. Clear? Let's move to the next slide. See, this is what is going to happen. Now the mold has begun to open. It has already traveled this far. See, the pin, the finger was here. It is moving straight up. Because it is cut at an angle, this is supposed to have a lateral movement, right? Lateral movement. Lateral movement. Hope this is clear. Now because the slides has drawn apart, it has got out of the undercut. Now you can inject the part. Clear? Now, we have only considered how to move it in, and how to move it out. We did not discuss about one other key point here. These fingers will only help to bring the slides in, and when it moves up, it will help to take the slide away. But consider, don't expect the fingers to act as a pressure applying element when the injection is taking place. What I mean to say is, see, these fingers are only meant to bring the slides in and to take the slide out when it moves in and up, right? You see the clearance here, see like a millimeter maybe per side. You can't have a H7G6 or a tight or a sliding fit for this purpose. So there is a clearance here. So what happens when the pressure comes in, the injection pressure comes in, right? It will give, it can move for this amount of distance. So what will happen, it will flash here, right? It can flash, it will definitely flash here. Because it will permit a movement of at least what is the clear, at least to the amount the pin is cleared for in the hole, right? So you can't expect the fingers to do the job of clamping the slits, the splits tight during injection. Definitely you need a back support. Somebody has to push it from the back, tail end, right? Now consider what you see in here is a arrangement made for that purpose here. Now it cannot move back. So mission accomplished? No. There is a limitation if you design it straight. Now let's see what will happen if it is straight. Okay. This back support is designed straight. Now what will happen when the slide is moving? Let's see that this finger is at an angle, right? The finger is at an angle. So this is slide. This is slide. Now we said we need a back support. So we have provided a back support of okay. We provided a back support here. Now just picturize, there is a clearance here probably for the finger. This is the main reason why we are providing a back support. Now mold is moving up. So the finger is going to move up, right? So finger will immediately when the mold moves up, it will push this here outside. So it is going to definitely push this away. Definitely going to push this away. But can it move? No, it cannot move because this is a straight line. It is on the way, right? Until this line covers this point. Until this line covers this point. Definitely something is on its way. So what is supposed to happen here? See here, something is on its way because it is straight line. When the finger moves up, it is not going to allow the slide to move out because a solid muscular support block which is straight in line is still covering the back of it. So what is supposed to happen? The weakest point will break. Probably finger is the weakest point here, element here. So it will snap, the finger will snap. So we learned that we can't have this line here, the tail end straight. We have to design it at an angle. See, we cannot have this straight. We have to design the tail end at an angle. That means this block will change the shape. It will be like this, right? Hope this is understood. Let's examine this. See, if when the back support is designed straight, what is going to happen is when the finger moves up, the slides immediately will try to move back out, but it won't be able to move out because there is something standing on its way. So definitely the finger is destined to break. Fingers are destined to break, right? So we have no choice. Instead of making it straight, we have to design the tail end at a angle. And what is this angle is a question which you should we should comprehend thoroughly. So angle, popularly used angle here, scientifically proven angle for the mounting the finger cam is 15. Sometimes there are cases you can move it up to like 18 or 19 degrees depending on the requirements, but commonly we use the mounting angle of the finger cam is 15. So just we learned from the previous slide that the tail end, if you design it straight, like if you design it straight right here, it goes here. If you design it straight, it is not going to leave any room for the slide to move out, right? So we have to design the slide, tail end of the slide at a angle. So this is the wedge. I will complete the wedge here. See, compare these two. A movement this high, no gap extra created. The same movement upwards, because it is at an angle, it will leave a gap here. See, there is a gap created, so nothing is stopping the slide from moving out. Clear? So what should be this angle? I already asked the question. What should be the angle of the wedge? What should be the angle? What should be the angle? It should be 0, definitely not good. So we learned from that slide, that particular drawing here. It should be at an angle. So it can't be even equal also. It will be 50-50 chance, correct? So we have to design it more than the angle which is provided for the finger cam. If the finger 15 degrees can push the slide for an amount of X, definitely any angle more than that will create more gap, create a more displacement than this particular angle here. So the tail angle here should be more than the finger cam angle. How much more? Generally, the tail angle. If this is 15, so the tail angle here should be more than the finger cam angle. This angle here, it should be. So 15, generally it is considered as plus 5 degrees. 5 degrees. So this should be 20 degrees. Hope you have understood this thoroughly. The need for cutting the tail end of the slides at an angle. It can't be straight. If it is straight, it is definitely going to interfere with the wedge, which is also straight. So you have to cut the tail end at an angle, and that relation between these two angles, the finger mounting angle and the wedge angle, is it should be 5 degrees. Wedge angle should be 5 degrees more than the finger angle. Hope it so far everything is thorough. Now let us look at arranging these things on the mold base, right? Definitely all these things comes in the on the moving side, like all the split cavities, and all the rails, everything is supposed to be coming on the moving side of the core. Let us see. This is how it is done. You, in order to, this is the slide which is supposed, you're supposed to make. You see a 5mm step cut. So you definitely cannot leave it open on a flat surface here. It should be in a track. So you create a track. So this is what you do. You create a with a channel with a slot here, and the size of the slot will be size of the slot here should be the relation here should be the fit, or the fit should be this here. This size should be a sliding fit. It should be a sliding fit in the slot. Slide fit. Slide fit. Why it should be sliding? You can't give too much of clearance and make it wobble around. What happens if you don't maintain this smooth sliding fit? Sometimes it can have a lateral movement on this side when it moves forward, or sometimes it can move to that side, leaving a parting line here. See, the parting line will look ugly. It will show a shift. It will show a shift as much when the clearance in the slide, the split and the slot in which it is sliding. For example, I'll just show you. Let's get out of this. Now look at this part here. You can see the well. I don't know whether it is visible to you. There you see this line here. But it's not very much visible in this part because it's well made. But what I'm trying to say is, so okay. So what I'm trying to say is, um, if you leave this relation open, like if you maintain a loose fit, the slide can move this way sometimes, it can move the other way sometimes when it moves forward. So the part is getting completed when the both side, left and the right hand side slides come and butt on this surface each other, right? So when it butts, it should make sure it is butting on the same periphery line, the complementing periphery line on its partner slide. Okay, so it is very important that when you build the mold, you have a smooth sliding fit, so you will have a repetition of the part. Now, the channel has been clamped on the core plate here, as you can see in the picture. The channel is clamped. You are used to 4 screws here, or maybe you can more, depending on your the, designing skills. Um, so you choose how much screws you want to put. Uh, so definitely it should be firm, and you keep the keeper plate. This is called the keeper plate, and the purpose of the keeper plate, this is called the keeper plate. Keeper. Keeper plate. Keeper plate. Now you see, you clamp the keeper plate on it, it will create a like a T shape here. Now the slide can move. This is when you install the core. See the next slide. See, now this is like a T shape here created. So the slide can be slid in, creating a good track. See, the left hand slide is removed for clarity purpose. So this is when the core is mounted. So now this is going to move in and out. And what is going to make the movement in and out is the finger cam hole, which is cut at an angle. When the finger cam goes up, it will push the slide out, right? And vice versa. When it comes in, it will push the slide in. So this is the arrangement on the bottom side. So this is how the sectional view will look like. See the finger mounted at 15 degrees, mounted at 15 degrees, and the wedge. So the angle of the wedge is 5 degrees more. So that means it's 20 degrees. Now we have cleared the core and the core plate in this case, so that the finger will not interfere with the lump of steel there. And what you see here is the keeper plate here, this line, this thickness here, and this is the thickness of the channel. Now just observe how it's working smoothly. It has already moved this far. The finger has started to move up, so it has already started to push this out. Because this angle is designed more than the finger cam angle, it will create a displacement, so that always a gap is there for the slide to come back. Okay, gap there. See, hope everything is clear. Now look at this slide. This is one other important point when we have to take care when you design. You see this here, a balloon view is here. It's called the ball catch screw. So you can have a springy ball here. When you it will pop up in and out, right? So what it is doing, it is the finger has gone disengaged with the, watch here, please watch here. The finger has disengaged from the slide, right, from the split. Now what will happen if accidentally, if this moves out, accidentally somebody touched a hand accidentally, so it moved out. So this portion has come here. That means there is no hole here, right? So when the finger comes back, it will not find this hole. Hole might have moved this way, and a solid steel is sitting here. So what's going to happen? You can just imagine what will happen, right? It will land on a place where there is no hole, where it cannot engage. So something has to break. Finger itself is the weakest point, it will break. So we don't want an accidental movement of the slide. So we have arranged a ball catch screw here, which will get clicked in the dimpling which is provided under the split. Hope this is clear. And why the mold will not be sitting the way you are watching on the screen. The mold will be mounted this way only if it is going in a vertical injection molding machine. Most of the cases it will be mounted this way, right? Horizontal. So just imagine, even due to gravity, it can fall down, right? Anyway, this is the worst case scenario. You should always have a stopper too. It's common sense. You can have a stopper here, but it will be on. It will be horizontally clamped, right? This will be more. It will be facing you. But if you, in cases if you have 4 slides, this is a possibility, right? And some of the designers use a spring mechanism so that it will not fall down. The slide which is on the top should not fall down. So you can have a spring loaded mechanism here too, right? Okay, so this is what is all about. The mold has opened. When the finger left the here, when the finger left the slide, the dimple has already clicked into that. The ball has already clicked into that dimple. So this is not going to move anymore. So which will help the finger to find this, engage in this hole when it returns back, so it is safe, right? And one extra thing you observe here is we have put another small wear plate here, a wear plate on which you can play on for fine tuning adjustments, right? And also once it is worn out, you only need to change the small little plate or shim it out to the right dimensions. Yeah. Now, there are some timing issues which you have to pay attention to. This is what it is. I already told you, when you, the purpose of the ball catch screw and the dimple arrangement is, this should click here the moment the finger leaves the slide, disengages with the slide. That means how much a movement the finger is going to cause on this particular slide is this here, right? This is the place where it is going to move up. So it will keep on pushing on this surface. That means you will have a lateral movement equal to, like in this case, it is 18 millimeter here, right? It is 18 millimeter. So that should match with your positioning the springy ball here, with the exact location. That means that should be 18 millimeter away. So what happens when the finger moves up? It will push the slide exactly 18 millimeter, and in that 18 millimeter, this ball will find its dimple here to click. Very important. And this is how the top plan view will look like. So what you see here is, this line here is the parting line of, this is slide number 1, and it's meeting each other here. This is slide number 2, right? And these two lines here is also important. So that is something like, if you look from the top, you will see this line here, which is this, and you will see this line here. That is the second line here. Similarly, on the other side, mirror, you'll see two lines, which is the tail end cut at an angle, double lines. And this line also is important. Now this looks like an ellipse. Of course, it has to look like an ellipse because the hole is cut at an angle, right? When you look from here, this here will look like an ellipse. Right? You already learned that in your engineering drawing during your first year. If a hole is straight, right, and you look from top, it will look circle, right? But if it is cut at an angle, when you look from top, it looks like a ellipse. Clear? Now, line here, this line here is the width of the slide, right? Because it is hidden under the keeper plate. This is the keeper plate which we used 1, 2, 3, 4, 5, 6 screws to clamp it down, and this is the keeper plate line. This is the keeper plate line. And this here, the dotted line, is the width of the slit. And this here is the ball catch which we discussed in the last slide. This here, the ball screw, 4 ball screws. And this here is the push-up pin, which has to push the ejector plate back to its position. And this will be the runner. So this is pretty much it is. Now just recap all the basic requirements. Sorry, before we have to discuss on one more point. What makes who governs the amount of movement of the slide? The question is, how much the slide should move out? Who is controlling that? Like this is the slide, right? It can move a distance of maybe x, or maybe a distance of x plus something. Right? Okay. See, we can observe from this. There is if your finger was to this length, slide pointer here. If your finger was designed to this length, how much it will move? It will give, definitely it will give more movement than a shorter length finger, right? See, just because this point will leave later than this point when it moves up, right? So that means it will keep on pushing. For example, if the finger is in the black line here, originally designed for this particular component, and how much it should be? It's just common sense. This you have a component of 30 millimeter, so per side it is like 15 millimeter. It should cover more than 15 millimeter, right? So in this case, it is designed for at least a moment of 18 millimeter. So if you want a longer moment, you just increase the length of the finger cam. That means it will give, in this case, for example, you see an extra moment of like 24 millimeter, right? If you had designed it to this length. Hope this is clear. And the mounting angle of the pillar is 15, and this should be 5 degrees more, that is 20. And you have a wear plate, and This is pretty much a 3-plate mold design. The split cavity mold is all about. And another thing which you have to be careful or pay attention to is this dimple here. The distance from here to the ball catch screw should be exactly to the amount we have designed the finger cam, the moment of the slide. Clear? Take a look at the fixed half arrangement. This filler is moved away for clarity. You cut two pockets here, and the tenon side of the your wedge block has to go and engage in it, locate. We screw from the bottom. You see the finger cam hole here. Finger cam hole here. This is the screw bush, and now the tenon portion has gone inside, maintaining the location. And screwed from bottom. You'll see a wear plate. You can have a little bit of fine adjustment with this wear plate if you want to, and you mount the finger cam in this hole here, and the top portion is complete. See? Now let us recap the whole learning with a few questions here. Context for the designing of a split cavity mold. A split cavity mold, it is when it is having a external undercut, right? What enables the movement of the split? The movement of the split is the finger cam. And what are the other means of moving the split? Sometimes we use a spring when the movement is very small, or sometimes we use hydraulic cylinders. What governs the amount of the split movement? That means a few slides back we discussed that if you want a longer movement, you increase the length of the finger cam and it will give you more movement. And what ensures the clamping of the splits while the plastic is injected? Definitely the fingers cannot hold the splits together tight when the injection is taking place, because it is not having a sliding fit with that supplementing hole in the, it is definitely a clearance hole, right? So it can move in that clearance and leaving a big chunk of flash. So definitely something has to be pushing the slides hard from the back side. So we provide a wedge. We provide a wedge at the tail end of the slide, right? What is the angle at which the finger cam is mounted in the fixed half? Usually it's scientifically proven 15 degrees, or there are instances where you go up to 18 or maybe even up to 20 depending on the requirements or the circumstances. What should be the angle provided the tail end of the split and the supplementing wedge? We have discussed this in detail, the necessity of designing this at an angle, and we know it should be definitely more than the finger cam mounting angle. So how much more was the question? How much more was the question? It's usually up to 5 degrees more than the finger cam mounting angle, right? So what is the arrangement of mounting the split on the core plate? It's the channel, and you use a keeper plate. You use a keeper plate so that the split will not pop out. What is the need for a ball catch click arrangement for the split? You understood when the mold, when the finger cam leaves the disengages with the split, we expect the split to stay where it is, right? If it is accidentally moved away, the finger cam is, when the finger cam comes back, it won't find the hole to engage with. So definitely it's going to sit on solid steel and break. So in order to ensure that it is remaining at the same parking spot, we put a springy ball, which is the ball catch mechanism, which will go and click in the dimpling provided under the slide. So this is pretty much with the like a split cavity mold. I hope you have understood everything thoroughly. Um, like you have any questions, please make sure you bring this up during the live online sessions now, and we will see more of these kind of videos in the coming days. Thank you very much. Have a nice day.